Now we understand how RSA method works. RSA method is very simple mathematics. All you do is exponentiation and mod. Right? The only difficulty is that the exponentiation is with a very large number of a very large number, and the mod is of a very large number. So these are all very large numbers, and that makes it difficult. And that's where the security comes in. And so the thing is, how can we calculate all these large things, and for which we have some help. So there are three things you can do if you are implementing RSA. Then you can compute some of these things beforehand and optimize. The first method you can optimize is to compute C raised to D mod P and C raised to D mod Q, because we are going to do n mod n, which is the product of two prime numbers P and Q. And so Chinese remainder theorem says that if you have any time a product for the modulus, you can break it into pieces. We saw example of 3, it could be 4, it could be 5, it could be 2. Right? It's moduli. So here in example, suppose you have two moduli, so basically two moduli. So you can calculate P and Q are a smaller number than n, you can calculate them and then use Chinese remainder theorem to calculate the product. Basically you will need some kind of inverse. You will need P inverse mod Q and Q inverse mod P. You can pre-calculate that, and that doesn't change. As a new plain text or ciphertext comes in, you don't have to recalculate that part. So once you know P inverse and Q inverse, then you can just calculate these little pieces and get the big piece. Well, that is the second thing, is that you do P inverse and Q inverse first. Okay. So third thing is, since D is much bigger than P. Why D is much bigger than P? Because we said that we want to keep the private key such that it cannot be easily guessed. Because if the private key was a small number like 2 or 3, people can just get 3 messages and solve the equation straight away, even if the other numbers are large. So D is, while E is small, public key E is small, the private key is large. So if D is large, then what you can do is you can subtract these P's as much as you can. So basically, instead of calculating C raised to D, you calculate C raised to R, where R is D mod P minus 1. This is very similar to the homework that we did, where homework was in chapter 8, not here. In chapter 8, we just saw this homework 23, mod 23, and power was 111. So we took out 110 out of that because P minus 1. So mod 22. So basically, whatever is the power, you can forget all the large powers. So this is the kind of thing I can ask in the exam, is that it can give you a number and a very large power mod something. Now you could do all the calculation, go all the powers of 2's, and that would be a long way to do it. But first thing you should do is reduce the power already, because you know that mod P minus 1, all those powers are equal to 1. So you can reduce that, and then you do the calculation using, squaring. And so if you get D, which is K times P minus 1 plus R, while D is large, you don't really use it, you just use R. And that is the Euler's theorem. And then only the private people can use this one, because public key people don't know P and Q. They know D and N, E and N, but they don't know P and Q. So you cannot use this optimization for encryption, but you can use it for decryption. All right. So RSA, what are the issues and attacks and problems? First of all, computationally intense, and that's the only way it is secure. Its method is very simple. There's nothing to be done, exponentiate and mod. But it requires lots of calculation, and simply because we use large number of bits, 1024 bits and up, plain text should be smaller than the key length, and then the plain text should be less than 1024 bits. If you are using key length of 1024, and the encrypted text is same size as the key length, so the mod will come out 1024 bits too. Right? So the answer will be same size as the key length. So this is generally not used for encrypting messages, but it is used to encrypt the secret keys. If you want to exchange a key with you, somebody had asked a question before, how do we send the key to you? Well, this is the method. If I have a secret key and I want to give it to you, I need your public key and my private key, and then we can do that encryption and we can send it to you. Once we both have that secret key, then we use DES or AES, that is much faster. The secret key methods are much faster in terms of computation than public key methods. So public key methods are used only for the key exchange mostly. And you don't want to do it for every block size. Alright, so attacks. Brute force attacks are kind of not possible unless the key is very small. Timing attacks are possible. Timing attacks try to guess whether your D is large or D is small, depending upon how long does it take for you to encrypt. Yesterday I was reading, totally unrelated stuff, but then it came up that quantum computers can do some of this much faster than this exponentiation and this and that. So they can break these things much faster than the regular computers. Quantum computers are not here yet, and I don't even know how they work, but basically when they come in, then much of this will be history. And chosen ciphertext attacks can work, because now this is simple exponentiation and so on and so forth. If somebody can just use the ciphertext and then can ask you to give the plain text back, then that can be a problem. So over time, what RSA has been doing is RSA has been running challenges. So here are the challenges winners. In 1991, 332-bit number, which is 100 decimal digit number, was broken by using 7 MIP ES. If you take a 1 MIP computer, that will take 7 years. If you take a 7 MIP computer, it will take 1 year by that method. Right? And 365, 398, 428, to keep on going, the last they did, now they have stopped actually this whole challenge. So last was 663, 200 digit number was done by using some kind of method. So they haven't put the power here, using this method, lattice sieve method. Now, what this method is, it doesn't really matter to us. Here, what matters is that slowly we are getting there. So if you use anything less than 663 today, you will be considered weak. And if you want to read all about it, it's all online. I found this URL, RSA Factoring Challenge Fact. And they have all the random numbers already written down. And the challenge, they don't have a challenge, means you won't get a prize, but the numbers are still there. You can still, there are numbers which have not been factored by anybody, and somebody can take a challenge. So one of the challenge was chosen plain text attack. And this is how it works. That if you take a public key, PU is public key, and you encrypt M, that will be equal to M raised to E mod N. So this is a linear relationship in the sense that if you take M1 and M2 and multiply them, that will be the same thing as encrypting M1 times M2. So what you could do is, you could take one bit at a time and send it, and then you can construct the whole message by combining those bits. Say for example, you multiply a number by 2, you know what this ciphertext would be. It will be simply 2 times E times the previous number. It will be just shifted by E bits. Right? So if somebody sent you enough number of this one, then you are in trouble. Right? So the thing is, so RSA obviously came up with a solution which is given here. This is slightly different than what is in the book, by the way, because the book gives a solution, but it doesn't really explain, how this works. So I went to Wikipedia, which has this picture, which is slightly different from the book, but it has a clear explanation about how it is working. So I am sticking to this one. Okay, this is called optimal asymmetric encryption padding, OASP. Basically what you're doing is you're padding the message so that nobody can play this game of shifting the bits. You always get full number of bits. So you're not just going to get M raised to E mod N, which could be a small number. You always get full 1024-bit answer. Okay? So you cannot shift by any number of bits that one. So that is what it is called, optimal asymmetric encryption padding. You pad your message such that the person who is trying to break it will need all 1024 bits and cannot shift it backward or forward or multiply or anything like that. Okay? So the way it works is, this is your message, which is less than your key size. Your key size is k. Your message is k minus k naught minus k1. So you need k1s of zeros, and if k1 is 0, that's fine. You don't need any zeros. And you need k naught of a random seed, k naught bits of random seed. And this seed is something that you will keep changing so that they don't repeat the same thing. Anyway, your k naught bit of seed, k1 numbers of zeros, and the rest of your message. You concatenate these two numbers, and you have two functions g and h, which are one-way hash functions, which are one-way, you can call them one-way hash functions. So that in g, if you give k naught bits, you get k minus k naught bits. In h, if you give it k minus k naught bits, you get k naught bits out. So there are two functions, g and h. One increases the bits, one decreases the bits. You take this seed, expand it to k minus k naught bits and exclusive r, and then you set that out as x. And you take this part here, x part actually, and you compress it using this function and send it out with exclusive r with seed as y, x and y. You don't send out r or m or 0 or anything like that. You just send out x and y. No, sorry. Now x and y, you don't send it out, I'm sorry. X and y is what you use to encrypt. So you encrypt x and y and then send them out, the whole thing. So there is no encryption here. So far the encryption is after this. So basically what this makes sure is that your message, becomes your message basically. This is your message. If you are missing any bits of this message, you cannot get back there. That's the whole thing. Because if you get the whole thing back, then you know what is your k naught size. That is known. Although you don't know the seed, but you know the size. So you run it through h function, an exclusive r with y, and you get the seed. You run it through g function, an exclusive r with x, and you get m and zeros. So you can get the whole thing backwards, provided you have complete x and complete y. If you have half of x, nothing happens. So this is why it is called optimal asymmetric encryption padding, is that this prevents this kind of attack where people shift and ask the answer. Problem is that this is very linear. People can do mathematical games and they can multiply the numbers and or they can shift the numbers and figure out what the plain text might be. So the solution that RSAs have selected is this one, is that they have padded the message in such a way that you need the whole thing before you can, so you cannot do this shifting or multiplying or anything like that. We are padding it like this. We are padding it with a zeros and then with a random seed combined, and this whole thing is now k bit long. K is the key size. Right? So you take this whole thing and you encrypt it with the key, whatever key you have. Right? Now if somebody tries to play the games like shifting the message or multiplying two messages, plain text messages, that they cannot do here because the padding would prevent them from doing that mathematics. I don't know. Maybe another simple answer is that x and y, h and g function make it somewhat non-linear as compared to that simple linear formula over there. First of all, let us understand this. The attacker doesn't really know, he knows all these functions, these are public information, g and h functions are public, and the seed is not public. Right? But attacker doesn't know x and y. What that means is it's not only encrypted values of x and y. Right? And they are trying to guess x and y by encrypting, by decrypting several things. Right? Every time they decrypt something, they will get an x and y, and the thing. They cannot decrypt it. They will have to ask you. They will ask you, okay, here is the ciphertext. What is my plain text? That is what is called chosen ciphertext attack. That I am the attacker and I choose the ciphertext. and then you give me the plain text back. This can be used, for example, in storage. I could, just probably ask for decryption or write something and get these other way around, something like that, right? So chosen ciphertext means I can choose the ciphertext, then I will give you X and Y, right? And so yes, you will get X. No, I will not give you X and Y. I will give you M back, right? And then you give me some other text, and then I will give you M back. So those M's you can get, but they will not satisfy this kind of formula, 2 raised to E formula. If we didn't do this, then what you will get is simply, things that you can just, bit by bit you can manipulate, and you can keep giving me ciphertext so you can keep guessing the next bit of the message. All right, so that finishes the RSA method of public key, and here are the 5 key summary messages. First of all, you should now remember is that public key uses 2 keys, one to encrypt, other to decrypt. One is public, one is private, but the keys are interchangeable. Interchangeable in the sense that you can use any one to encrypt and the other one will decrypt. So that is the general public key encryption method. And we will talk about in the next chapter that we are getting into now. We will talk about other public key encryption methods. All of them have this property. However, RSA shows a particular function, exponentiation in the Galois field n for large n. N is not prime, n is a product of 2 primes, remember. Right? They selected Galois field n for large n and to do this public key. RSA keys are therefore E, N and D, N, where E, D marks phi, N is 1. So basically you find out the quotient function for n, and then E times D equal to 1. Given the keys, both encryption and decryptions are very easy, but if you don't have the keys, then it is very difficult to find the other, given the one to find the other. The message size should be less than the key size, and therefore you need large keys, and I should probably, as I said, universally change 512, which is equal to 1024. This is the example. We can actually, so here is an example, similar to the example work. So you take 2 large primes. This example we take 17 and 11. You multiply the prime, that is your n. 17 and 11, 187 is your n. You calculate the quotient function for n. Now remember, this is another thing, is the quotient function for n, but the product of primes is basically product of the quotient functions of those numbers. So quotient function of n is equal to quotient function of p times quotient function of q. For a prime it is p minus 1, so it is p minus 1 times q minus 1. 160 is the phi. Now this is important to be able to calculate phi. Once you have calculated phi, then you factor it out. And you have to find an E such that it is relatively prime to phi. So 160 means what numbers cannot be E? 2, 4, 6, 8, 16, 32 times 5. 160 is 32 times 5. Right? So 2 and powers of 2 cannot be E. And 5 cannot be E. Right? But other numbers such as 3, 7, could be E. So we select 7, we could have selected 3, but we select 7 and then we want to find D such that DE mod phi is 1. So what we multiply to 7 so that we get a 1. Now to get this thing, again you need to do the table. If phi is a small number, then you don't need the table. So here I would use the table, although like as shown here, in this example, we wrote down all the products of 160 plus 1. So 161 is 1 mod phi, 321 is 1 mod phi, 481 is 1 mod phi, 641 is 1 mod phi. Right? And therefore, we are looking for something that divides 7. So it turns out that 161 is divisible by 7, and therefore 23 is inverse of 7. Okay, you multiply 23 and 7, you get. Yes, so now you have 2 keys, 7 and 187 is the 1 key, and 23 and 187 second key. Right? So all the AES keys have two parts. The first part is used for exponentiation, and the second part is used for mod. So whenever you have a message, you want to encrypt it, all you do is raise it to the power 7 and then mod 187. When you want to decrypt something, you raise it to the power 23 and do mod 187. Or the bigger thing is, if somebody could factor out 187, then they're done. So the thing is, we can factor out 187 to 17 and then 11. Once we know 17 and 11, we know P and Q. Then we know we can figure out the other key to basically factor out. That's why RSA has this challenge where they put down number and say, okay, here is challenge, you can factor this out, and people do 7 years, 5 years, 2 years, 2 years, all that, right? So that is the challenge, is that these numbers are very large, and even the best scientist in the world cannot factor it out for, in the short